So welcome to the first guest lecture in Professor Pascal Poupart's reinforcement learning course. My mic is not working, so I will just shout. So if you don't hear me, just let me know. So I'm one of his PhD students working on dialogue systems and conversational agents. And this is also the topic for today's talk. And I'm also a data scientist, a part-time one, at Pronav Technologies, which is a local startup. So Pronav so their main product is a dialogue system for the insurance industry specifically. So they develop a dialogue system which is deployed on the website of insurance companies. So when you go to the websites of these insurance companies, you will see a chatbot on the side and you can chat with it. It will help you get insurance quotes. It will answer your frequently asked questions and so on. So the agenda of today's talk is I will talk about dialogue systems in production, and I will also talk about dialogue systems which are built using more cutting-edge techniques in deep reinforcement learning. So today's outline is as follows. I will introduce to you what dialogue systems are and how they're categorized. I'll introduce Pronav Technologies to you in a bit more detail and what their technology looks like. We will look at some traditional machine learning and natural language understanding algorithms for dialogue systems. And then we will look at deep reinforcement learning for dialogue systems in more detail. So what is a dialogue system? It's basically an artificial agent that can carry out spoken or text-based conversations with humans. Examples are Alexa, Siri, Cortana. These three are all spoken dialogue systems. But for the purpose of today's talk, we'll just assume that we're talking about text-based dialogue systems. So text-to-speech is another problem that is solved by other techniques. So that's just an add-on feature over text-based dialogue systems. Dialogue systems are also called chatbots or conversational agents in the literature. And there's one main way of classifying them. There are retrieval-based dialogue systems and generative dialogue systems. So retrieval-based dialogue systems, as the name suggests, are dialogue systems that retrieve their responses from a pre-built database of responses. So these retrieval-based systems will not make up sentences on their own. They will simply pick one out of a database that you as a developer built for it. Generative dialogue systems, on the other hand, are more agile in the sense that they will generate sentences from scratch, word by word. So they will make up sentences on their own and so on. And here's a more detailed look on what retrieval-based dialogue systems look like. So we have a user chatting with a dialogue system. So they say something like, I want an insurance quote for my car and my home. So this input text will go in this module, which is the natural language processor. So this uses some machine learning techniques, traditional machine learning techniques, for instance, to parse the input text and figure out what the user wants. So that's encapsulated in this thing called intent. So here the user wants some quotes, so the intent is get quote. And then we also want to extract some keywords or key phrases from the input text that help us decipher what the user wants. And in this case, the keywords are car and home, as opposed to life insurance or some other type of insurance. So once we've understood what the user wants, we can pass this information to what we call a dialogue manager. And the dialogue manager is essentially just a bunch of if-else statements. If the intent is this and this entity is found, then produce this response. And the responses are pulled from a database of responses. So you as a developer will put in all possible responses that you want your bot to say, and it will say those. So this output is retrieved from this database. And here is a picture of a generative dialogue model. Here, the entire system is replaced by a single neural network, which is a recurrent neural network. So if you don't know what a recurrent type of neural network is, that's fine. You can just imagine that this is a regular feed-forward neural network. So this big RNN consists of two smaller RNNs. One is the encoder RNN, the other is the decoder RNN. So the job of the encoder RNN is to look at the input sentence and summarize that information in a single vector, which we call the context vector, which then goes into the decoder. And decoder will generate the output response on its own, word by word. Okay. And now we see some comparisons between these two systems. I should mention here that most systems in production today are retrieval-based. I say most, not all, because we're getting there now, gradually, where we have generative dialogue systems in production. First one, so retrieval-based dialogue systems are trying to solve machine learning problems that are generally easier than the one that are being solved by the generative one. So in this case, the input is a sentence, and output will be some label, intent or entity, and these are only a few hundred in number. Whereas in the generative case, the input is a sentence and the output is also a sentence. And then the output sentence can be as long as you want it to be, so it can be infinite basically. And then if you have a big vocabulary or a big dictionary, then every single word that it generates will be a probability distribution over thousands of words in your dictionary. So it's a very hard problem. It's a much harder problem here than over there. Predictable responses, unpredictable responses, that's obvious because over there the responses are all pre-programmed. And that's why number 3 is also true, easier to control behavior compared to hard to control behavior. Don't need tons of training data. Tons of training data required here. So, we need, generally recurrent neural networks need a lot of training data just due to the way that they're designed, but also due to the fact that the machine learning problem itself is much harder and needs more data. We need many more if-else rules in the case of retrieval-based systems, whereas here we don't need any if-else rules. So the network will take care of all that implicitly for you. So, and over there, for retrieval-based systems, if-else rules can grow exponentially. So they can be harder to manage as a developer. If you want to add one more rule, you have to look through a whole bunch of previous rules to make sure that a similar rule doesn't exist. Or if you want to modify something, a previous rule, then it's really hard. Do not generalize well. These do generalize well, again, for obvious reasons. This is generated on the fly. So we're going to look at retrieval-based dialogue systems first. And what I'll do is I will look at some of the traditional machine learning algorithms that are used to solve the problems of intent and entity detection. Okay, so the first question is, given a sentence, what is the intent of it? Like I mentioned previously, intent here simply means a label of what the user wants from the system. So sentence like, I want an auto insurance quote is obviously a get quote. Whereas a sentence like, do you sell policies outside Canada? This is more of a frequently asked question about location. So that's what the label would be. And then the entities are, like I mentioned, some keywords or key phrases within sentences. So here, car and home are entities. Right. So for intent classification, here in this slide, I've just put some samples or some example of what the data would look like if you want to train it. So the input would be a bunch of sentences, and the output would be a label for each sentence. So the labels would be of this form: get quote, get contact info, FAQ location, and so on. And in the case of named entity recognition, the problem is given an input sentence, you want to produce a label for every single word in that sentence. So every single word in this sentence could be an entity potentially, and we want to map them to the right entity. So the words like do you provide will map to null in this case because they don't give us any information, but the word car insurance, the phrase car insurance will map to insurance type. Similarly, Ontario would map to province name. So we want the system to recognize auto insurance and Ontario as the entities in this case. So the next step is what should be the features for these machine learning algorithms. So if you recall, before the advent of deep learning, in simpler times, machine learning algorithms required some feature engineering. So you did need data, but you also needed to specify how to extract features from them. So the latest way to do that is through word vectors. So you might have heard of Word2Vec or glove vectors. So Word2Vec was developed by Google some time back, I believe. And the idea there is that each word should be mapped to a vector, and each entry in that vector should have some semantic meaning about it. So traditionally, before the advent of Word2Vec, we used to have one-hot encoding of words. And what happened there is that for each word, you would have a vector of length the size of your dictionary. So if your dictionary had 5 words, say king, queen, man, woman, and child, then each word would be represented by a vector of length 5. And there would be a 1 somewhere in the vector and zeros everywhere else. So king, for example, would be the vector 1, 0, 0, 0, 0. Queen would be 0, 1, 0, 0, 0, and so on. And the problem with that is, so who can tell me what the problem with that sort of encoding is? Sorry?
Dictionary has to be large.
You're only setting one bit, it's sparse.
No semantic between, there is no relation between the words and its representation.
Right. So somebody said dictionary has to be large, but that shouldn't be a problem. Dictionary is usually very large. I'm not sure what the second answer was.
Sparse, it's very sparse.
It is very sparse, yeah, but yeah, that could also pose as a problem. But I guess the biggest disadvantage is that there's no meaning. There's no way of relating the meaning of those two words. So if king is 1000 and queen is 01000, just looking at the vectors, you cannot tell which one was which, or how do they compare with each other. So what Word2Vec does is it makes sure that each entry in the vector has some abstract meaning attached to it. So for example, the first element in the vector here could correspond to royalty. I'm sorry if you cannot see this clearly, but this is royalty, masculinity, femininity, age. So for the first entry, royalty, king, queen, and princess would have higher values, and woman would have a lower value. For masculinity, which is the second entry, king would be the highest value, queen, woman, and princess would have lower values. And it's interesting that queen has higher masculinity than woman and princess, but I think that's just, oh yeah, and the last thing is which classification algorithms to use. Typically, production dialog systems use support vector machines for intent classification and conditional random fields for entity detection. So I'm not going to go in more detail of these algorithms. So we're just going to move on. Right, so the challenges with retrieval-based systems, like I mentioned before, is that it will not generalize well. So here is one message that one of Pronav's insurance bots received. So this is a real message, and it's a really, really long one. So as a human, you would probably take some time to read it, and understand it, and you will probably still not understand what the user actually wants from here. So here there's a person just complaining about insurance companies in general. So what they're saying is that they paid insurance for 40 years and they never had to file a claim. And then after 40 years of paying insurance, they finally had to, there was a situation where they had to pay a claim, they had some issue, and then their insurance premium got really high. So they're just complaining in general. They don't want the bot to basically solve their problem. It's just, and it's hard to parse these long sentences. And then another problem is unique messages that you haven't accounted for in your if-else statements. So here the person is saying, I would like a quote, but my number 6 is not working, so I could not complete my postal code information. And you can imagine that you would never have thought of this if you were, as a developer, writing the if-else statements, right? You probably won't even have this in your data for intent detection. And actually, it's not clear what their intent is. They do want a quote, but they're not able to completely give us the information, so what to do in this case? These cases are not well handled by retrieval-based systems. So some of these challenges can be addressed by reinforcement learning. And what I'll do next is talk about how to incorporate deep reinforcement learning in dialogue generation, in retrieval-based dialogue, sorry, not generative. So the contents of the next few slides have been taken from this paper, Continuously Learning Neural Dialogue Management. So this is up on arXiv from the year 2016. So this is a retrieval-based system, and the domain is, well, the application is a dialogue system that provides information about restaurants in a particular area within England. So the domain is 150 restaurants, and each restaurant has 6 slots or 6 pieces of information associated with it. So each restaurant has a food type, area, price range, phone, address, postal code. And what the bot will do is it will query the user about these 3, food type, area, price range, to constrain its research, its search space. And once it narrows down on the search space, it can pull out actual restaurants that the user wants and display these 3 properties of those restaurants: phone, address, and postal code. So the immediate goal of the system is to first determine what the intent should be of the system's response, and also which of these slots to talk about. And then once you know these 2 pieces, you can pull the right response from the database. And this is a picture of what their system looks like. So this is a neural network, and the individual items in that network have been defined over here. The input of the network is a dialogue belief state, which encodes the understood user intents plus the dialogue history. So a bunch of previous messages in the dialogue, and also the intention of the user, which you can presumably compute through some other machine learning algorithm, or not. Okay, so this is the policy network, and it contains one hidden layer with tanh nonlinearities. The output layer, which is this one, consists of 2 softmax partitions and 3 sigmoid partitions. So over dialogue acts and query slots, it's going to have a softmax distribution, and over the offer slots, it's going to have binary sigmoid type partitions. So dialogue acts are request, offer, inform, select, buy. So the bot will select which one of these it wants to proceed with, and then it figures out which one of these query slots to query the user with. And finally, if the bot wants to offer something to the user, it needs to select which one of these to talk about. So you don't have to go in too many details. The main point to take from this slide is that if you know the user's intent, if you have computed the user's intent and you know the dialogue history, then you can input it through the hidden layer, and the output will be a combination of softmaxes and sigmoids over the different items that you want to predict. So the database here just pulls out the restaurants from the domain once you have constrained your search space. Any questions about this this system? Okay. So training in this case, actually in most papers that you will find on deep reinforcement learning for dialogue systems or for NLP, you will find that training is done in two phases. So the first phase of training is supervised learning, which is where you've been given some labeled data, input, output, sentence pairs, and you just pass it through your network and try to maximize the likelihood of the output given the input. And that's what is done here as well. So they collect some language or dialogue data about the restaurant search using Amazon Mechanical Turk. So they've collected 720 dialogues, and they run supervised learning using the same neural network. The training objective is maximize the likelihood of data. And the second phase is reinforcement learning, where they change the objective function of the network to maximize expected reward of dialogue. So if you look at this objective function, what it's doing is it is summing up the rewards for each episode. So an episode is basically a dialogue exchange between some user and a bot until the conversation is over. So you sum up all the rewards from that conversation, and you want to now maximize the expectation of that reward given the policy. So pi theta here is the policy, which, can someone tell me what pi theta would be in this case? Not you, you're the TA. Can someone else tell us what pi theta is in this case? Yes.
Policy parameterized by the West.
Right. So the neural network itself has parameters in it, and those parameters constitute the policy. Using those parameters, the network outputs what action to take next. That's why the neural network itself is the policy. So just the network and its parameters itself are pi theta in this case. And then the next question is which algorithm to use to solve this reinforcement learning problem. And the answer is something that we haven't seen so far in this course. It's policy gradient methods. So policy gradient methods, I will briefly go over them. Pascal will talk about them in more detail in lecture 7a. Yes?
Do you know how they define the reward signal for this problem?
I think it's really about task completion. So if the user is satisfied and they got some answer, that's +1. And then maybe if the bot lost track of the conversation or gave some restaurant that the user didn't ask for, that's bad. So that's -1. Yes?
Go back to this. In phase 1, what is the model we use to maximize likelihood?
I'm not sure what they use in the paper, but it can just be the negative log likelihood or cross entropy loss or whatever. Yeah. So you can use any type of objective function there. Yes.
Do they use the same network, like this one or this two?
It's the same network, yes. Yeah, so the network doesn't need to change. They just change the objective function.
As the high theta is just a neutral network. That's how should we train the neutral network? Depends on this equation.
Okay, so we will have, okay, so in phase 1, we did train the network on the data, right? So that was a supervised learning setting. And when we trained the network with that, we did change the parameters, right? So now we have a bunch of parameters that have been trained using supervised learning. So we continue learning on those parameters. And at every step, the existing state of the neural network or the existing values of the parameters of that network are the policy.
But I suppose that's just for this equation, as your purpose is to maximize the J theta, right?
Yes.
So that's the training of the neutral network should be one part of this equation.
So you're asking how the pi theta would be updated?
Yeah, I mean, because for this equation, we need to use the iterative solver to guess the pi theta. And well, in the iterative solver, the pi theta need to be trained. So I don't know how do you combine them together.
I'm not entirely sure what you mean by pi theta should be trained. It is trained, but maybe we can take this offline. So there are many details in the paper that I have not mentioned in this presentation, and we can talk about that after the lecture, right? So here, all I'm saying is that the objective has changed. The objective previously was to maximize the output likelihood given the input sentence, and now it's just maximizing the reward. So that's all I'm saying in this slide. And I do need to describe to you what policy gradients methods are. Like I said, Pascal will talk about this in lecture 7a, which is a few weeks from now. But essentially, the problem that policy gradient methods solve are how do you calculate how do you maximize the expectation of reward given some policy. So the intuition here is that you will collect a bunch of trajectories or episodes using your policy. Maybe you have two virtual agents that are interacting with each other using this policy pi theta. So you collect a bunch of episodes, and then you try to either make the good trajectories more probable, or you try to make the good actions more probable, or some other combination of these two or some other mechanism. So that's the basic intuition behind policy gradient methods. I will not go in more detail here because there's a whole lecture coming up on that. Is that okay? Okay, so that's all I'm going to say about retrieval-based systems. So for retrieval-based systems, we looked at some traditional machine learning algorithms that do intent and entity detection for us. And then we looked at some deep reinforcement learning techniques to help with that. And now for generative dialogue systems, I will quickly show you the picture that I showed you previously. Here, a user is interacting with just a neural network. And that's it. There are no other components of intent or entity detection. And the most commonly used framework for doing this in practice is sequence to sequence. So I say that here. Sequence to sequence is a framework developed by Google in 2014. And what they do is they have, like the previous picture showed, an LSTM encoder and an LSTM decoder. So it's the encoder-decoder architecture we saw, but now the individual cells in the hidden layer are LSTM cells rather than some other generic cells. So LSTMs are long short-term memory units. So it's just a different type of non-linearity that you can have in your network. So instead of tanh, you can use LSTMs. And the training objective for sequence to sequence, if you're doing it in a supervised way, again, is maximum likelihood of the data. So you maximize the likelihood of outputs given the inputs. And then there are challenges associated with the generative dialogue systems as well. and in particular sequence to sequence, the problems are, they're likely to generate short and dull responses, like I don't know or I'm not sure. They are short-sighted, so they're only based on a few previous utterances. And they will never look forward like reinforcement learning does. Maximum likelihood objective is not how humans converse. So when humans converse with each other, they have some other goals in mind, not maximum likelihood. In the fully supervised setting, you need a lot of data to train recurrent neural networks and sequence to sequence in particular. So you need at least 500,000 input-output pairs for this to produce something decent. Right, and the problem with requiring so much data is that you will typically not find so much data on every single domain and topic. So for example, in the restaurant domain, we saw that the authors collected 720 dialogues using Amazon Mechanical Turk, which is a very small number, and Amazon Mechanical Turk is not free. So I would imagine that they were constrained by time as well as money. And then you will also spend several days training sequence to sequence to get a decent enough system. And the main reason for this is you need to tune some hyperparameters. And in general, RNNs are crazy hard to train. So what I will do is I will present another paper, some details of another paper. So this is deep reinforcement learning for dialogue generation, published in EMNLP 2016, which is really, really old by today's standards. This is by the group over at Stanford. So this is a very famous seminal paper that talks about DRL for dialogue generation. So the claims they make are that they will model the long-term influence of a generated response in an ongoing dialogue. They define some reward heuristics to better mimic real-life conversations. And the way that they set up their experiments is that they simulate conversation between two virtual agents. So two copies of your sequence-to-sequence system chatting with each other. And then they can explore the space of actions while they converse. And then the objective in this case is also maximizing expected reward. So you can use policy gradient for that as well. And in this setting, we will not be talking about any task-oriented dialogue system. So there's no task involved that the bot has to solve. Previously, it was supposed to pull out the right restaurants given the user's request. Here, it's just open domain, just regular chit-chat about whatever, okay? So the goal, I guess, is to entertain the user, just keep them engaged and so on. Right, so the state in this case would be the concatenation of previous two dialogue turns, which will be considered to be input to the encoder. So in the picture, we saw that a single utterance goes as input to the encoder. Here they considered two previous messages to be the input to the encoder. The action that the bot needs to perform is generate a dialogue utterance. And this is essentially infinite action space because your utterance can be as long as possible. So you could the decoder could keep generating words one after the other, and in that sense, the action space is infinite. And the policy that we want to optimize is stochastic, and it's given by this expression. So probability sub RL. Given the previous two messages, you want to generate the next response, which is pi plus 1. And right, so again, the parameters of the encoder-decoder neural network are the policy itself. So we're going to train them as we go. Right, and the question is reward. So can anyone tell me what reward function we could use in this setting? So this is open domain chit chat, some entertaining chat that the bot wants to do. So what would be a nice reward function? Yes.
One could just be supplied by the user about whether they're enjoying their conversation.
Right. So we could have the user give us a thumbs up or thumbs down. That's good.
Clarification, yeah.
Right.
When
Or,
you
or
suggest
some
the
emoji that the user can type. What else? Yeah.
Time spent on the platform?
Time spent in each episode. Right. That's another one. Okay. What else? Okay. So the two that we just got, they are like traditionally used reward systems for dialogue systems. So even before the neural networks arrived and we had these old MDP-based dialogue systems, we would use these reward functions to estimate how good the conversation was. So interestingly, this paper defines 3 more reward functions: easy to answer, non-repetitive, and semantic coherence. So I should mention that these are all heuristics. Some of you might not agree with these or how they're formulated, but the paper shows that we can define these in mathematical equations and then we can optimize them, and that actually helps. So in the next few slides, I will go through each of these 3 reward functions and see how they define it. So ease of answering means that the bot's message should be easy for the user to answer. And the way they define it is the negative likelihood of a dull response. So if the bot produces a dull response, that's hard for the user to respond to. So the higher the probability of generating a dull response, the lower the probability that the user would be interested or find it easy to answer. Hence the negative sign. So there's a simple way to compute the reward based on this. We can just manually define a set S of responses that we think are dull. So this would include stuff like I don't know, or I'm not sure, or whatever. And then we define the reward as follows. So we compute the log probability that the neural network will produce a dull response S given the previous action A. And then we sum this probability up for all possible dull responses in our set S. And then we're scaling it by the length of the dull response S as well as the number of elements in the set S. So I mean, these scaling factors are just there to make sure that things scale properly. The gist is that we're just summing up these probabilities of generating the dull responses, and we have a negative reward every time this probability is high. So does this make sense to everyone? Okay. So the second reward that they mentioned was non-repetitiveness. So non-repetitiveness means you want to avoid responses that are too similar to each other or just identical to each other. So they call this as high information flow. So every message should be very informative and have high information content. And that's relatively simpler to compute. You just take the previous message that the bot sent to the user, and you compute its cosine similarity with the message you're about to produce, or something like that. So this is just the formula for computing the cosine similarity between 2 vectors. And these 2 vectors are just the encodings of the 2 sentences the bot produced. So HP is the encoded representation of utterance P, which you can compute using the encoder of your neural network. So the higher the cosine similarity, the lower the reward would be, or the more negative the reward would be. And then the last one is semantic coherence. So this means that the the bot's response should have some semantic overlap with what the user said previously. So there should be meaningful overlap between what they mean. And the heuristic they use here is that they will measure the mutual information score of 2 consecutive messages between the bot and the user. So there are 2 components of the reward function. First, you will compute the probability of generating some answer given the previous dialogue history. And then you will reverse that. So you will compute the probability of generating the previous message given the current message. So backward here means you simply train your neural network, a separate neural network, on a data that has been reversed. So this is one neural network, and this is another neural network. And for this one, the data set has been reversed. So all the outputs have become inputs, and all the inputs have become outputs. So you do need to train another neural network to compute this reward function. And then there are some more technical details in how we can backpropagate through this sort of reward function. And you can find those in the paper themselves. So I will not go over that today. So is that okay? Yes. It just means that, yeah, you're right. Essentially, you want to nullify the effect of the length of responses. That's why you scale them by the length of the responses. So you only want to look at the semantic coherence, and you don't want any differences in length to play any role in this reward function.
How can that balance happen? Like the probability is at most 1, right? So why does that 1 over n will cancel the influence of the length?
I mean, you're adding a bunch of probabilities, so you might go above 1, right? So that's why. I mean, here you have log though, so that will not happen. But the idea is not to go above 1. The idea is that you don't want the differences in length of these two to play any role in the reward. So the typical strategy is to always normalize by length. Yeah.
So if the answer is longer, then the log will be greater.
It's possible. It's possible that a longer response would generate a higher probability, even though it's a low reward sentence.
How could that happen? Like, how do you define the sequence-to-sequence probability? Can you show some formula to say it's greater if it's longer?
So let's take this offline. I feel like I'm not understanding your question properly, and we can talk offline after the class. But yeah, so broadly speaking, we typically scale by the length of the responses because we don't want differences in length to play any role in the reward calculation. The reward calculation has to be solely based on the semantic coherence between 2 messages, rather than any noise added due to differences in length, right? Any other questions? This is basically the last slide of my talk. So I'm just going to quickly mention that the final reward function is a weighted combination of the 3 rewards we just saw. So these are just weights that can be hyperparameters. So you have to tune lambda 1, lambda 2, lambda 3, such that they sum to 1. And then the overall strategy of training is, again, a 2-phase training approach where you first train your sequence-to-sequence system with maximum likelihood objective. This is supervised learning. And then you go to the reinforcement learning objective where you want to maximize the reward collected over a bunch of trajectories that you collected. And then you want to use policy gradient methods to optimize that, maximize the expected reward. Okay, so in summary, we looked at retrieval-based systems, and we looked at traditional machine learning techniques to do supervised learning. We looked at neural network-based techniques as well, which use two-phase training approach, supervised learning followed by reinforcement learning. And then we saw generative dialogue systems. Most of them are neural network-based, and they also follow the strategy of supervised learning followed by reinforcement learning. Another reason for doing supervised learning before reinforcement learning is that you don't want to start off doing reinforcement learning on a bunch of randomly initialized parameters. So it's good to use your supervised learning to get some base parameters that are decent, and then you continue improving them through RL. And some active research areas in this domain of dialogue systems are RL-based transfer learning for them, as well as RL-based emotional dialogue systems. So these are up-and-coming areas in research. So if you want to talk to me or Pascal about them, or you want to do your project on one of these, you're welcome to come and talk to us. I will also mention that ProNav is hiring. So they are looking to hire software engineers, NLP engineers, data scientists, and you can find more details on their website. So you can, this is like a free publicity that I'm doing for them. So you can email me, or you can directly apply on their website to see where that goes, all right? So that's it. I'm letting you guys go early.